Okay, let's get started. Okay, today what we're going to talk about is a little bit different topic. So far we looked at how to use the microprocessor 8051 and how to use the interrupt and serial communications and timers in order to use microprocessor with some other external devices, and in order to use that as a microcontroller and how to enable or disable the interrupt and those things, right? Today what we're going to talk about is some of the basics, like some of the concepts of a microprocessor and what kind of new technology that are introduced in microprocessors. The processor so far we use the 8051, which was developed like 30 years ago. So the microprocessor has developed, right, has been evolved into a recent processor, which is 32 bits. So in the recent processor, we have a lot of new technologies built into the processor, right? So that's some of the concepts we want to learn. You know, what kind of new things, new technologies, new advancements are built into our recent microprocessors, okay? So first of all, I think we already discussed these things, but we want to remember that what would be the difference between the microprocessors and microcontrollers. Remember that I give you the illustrations of a human being, right? In human being, microprocessor is like a human, we use a lot of brain, right? Someone, like some human wants to use a lot of brains to do a lot of jobs. So in this case, right, microprocessor is something like a CPU in your PC. Your PC is actually designed to do a lot of calculations and computations, right? So you need a lot of CPU power or processing power, okay? So this microprocessor typically has a lot of processing power. So therefore, you want to have a high performance like Intel processors, right? So that's the main thing, high performance, and how to calculate faster, okay? That's the main goal of the microprocessor. However, microcontrollers, it's like a human being with a lot of hands, right? So the focus is not to calculate a lot of difficult job, but in this case, what you want to do is you want to control the many other external devices. So therefore, in microcontroller, we probably don't want to have a lot of fast clock, but we want to have a lot of interfaces, like external interfaces, interrupts, a lot of timers, okay? So some of those things, or serial communications, things like that. So that's the microcontroller. Somehow these two are similar, but that's the main difference. So therefore, in microprocessor, you see a lot of Intel processor, things like this used in PC. Rather, in microcontrollers, you see these like something like this. ARM processor, 8051 or AVR, and these are the microcontrollers, okay? So what I'd like to introduce to you is some of the state-of-the-art technology used in microprocessors or microcontrollers, such as these things. So we're going to look at one by one. So first thing to look at is a super pipeline. We already looked at the pipeline concept, right? We already learned what is a pipeline. So let me remind you what it was the pipeline. The pipeline is like you have 4 different stages. What are the stages? First of all, you want to do fetch. Okay, there was an instruction in the memory in the binary format, and from the microprocessor perspective, what you need to do first is a fetch. Read the instruction. That's fetch. And second thing is that you need to look at what instruction you already fetched, right? What instruction you have. That's a decode. And once you decode it, now you know that okay, this is an add instruction. Then you need to add it really, execute, right? That's the third step. The last step is that when you add it or any other execution, there will be a result. So those results need to be stored back to the memory. So that's a save or store, okay, or save back. That is the 4 different stages. In this super pipeline, what they're trying to do is they increase the number of stages. It's not 4 stages, but 8 stages, or some other processor such as the Intel processor these days, they sometimes have 16 stages. So if you have a more and more stages, okay, then nice thing about these things is that somehow you make in this case, right, when you have 8 stages, you can actually have the 8 different instructions somehow in parallel. Okay, so this is a pipeline, and 8 instructions can go into the pipeline. So in order to make a full pipeline full, okay, you need 8 instructions. So somehow 8 instructions can go parallel. If you increase it into 16 stages, now you can see that there are 16, okay, pipeline stages. So therefore, you can have a 16 instructions at the same time. Okay, that's the super pipeline. So benefit of this is that since you have more instructions in the pipeline, you can actually execute more instructions in parallel, right? So performance is higher because you actually, that's called a parallelism. Okay, you have many things in parallel, so you increase the parallel instructions. So that's a nice thing about this. However, as I mentioned earlier, basic assumption when you use a pipeline is that all these instructions in the pipeline should not be dependent. Okay, all these instructions in parallel needs to be independent, right? Remember that? So the first instruction is such as like add a accumulator with R0. Let's say you have some value in accumulator, you have another value in R0, and first instruction is addition of A, accumulation, and R0. In that case, all the other instructions in the pipeline should not use A and R0. Right? R0 actually is fine, but all the other instructions should not use accumulator because the first instruction is using the accumulator and change the value of the accumulator. Okay? So all the other instructions should not use that. So that is independence, right? If some other instruction in the pipeline is using accumulator, then everything is messed up because this first instruction is going to change the accumulator, but before changing the value, the other instruction is actually using accumulator, right? So it's messed up. So that's a dependency. So you need to make sure that there is no dependency. But think about that. You increase the stages. Now we have 16 stages. Then all these 16 instructions should be independent. So that's a little bit tough to do it, right? So that's a little bit something that you want to be careful about. Okay. Other than that, this one is one of the technology to improve the performance. For high performance, you want to increase the pipeline stages. Another thing is called a superscalar. This one also looks almost similar as a pipeline. In this case, it's actually 5 stages: fetch, decode, and execute. And mem means memory, and write back. So somehow they split into 5 different stages. It's okay. I mean, it can be 5 stages or 8 stages. You know, you can decide how many stages you have. But in superscalar, it's actually different from regular pipeline. And how it's different is that in the regular pipeline, you have one pipeline chain here, right? We have 5 stages in one, and the next one is actually shifted by this, right? So you have this one, and this one, this one, this one, this one. That's a regular pipeline. But in this superscalar, what happened is you have 2 of them. You have two of the pipeline chain here in the same stage, and another 2 in the same stage, 2, same stage, 2, 2. So somehow this superscalar is same as there's 2 different hardware. Each one is a pipeline. Okay, we have one regular pipeline hardware. We have another regular pipeline hardware. So we have 2 different pipeline hardware. Okay, so for this one and this one, this one, this one, this one, that's for the first pipeline hardware, and that one, this one, this one, this one, this one, that's for the second pipeline hardware. So you have a multiple pipeline hardware. In this case, this is the example of only 2. Okay, 2 independent hardware. So that's a superscalar. So it's like multiple pipeline stages. You see the difference? This one is like you have a one pipeline hardware. Okay, we have a one pipeline hardware, but we have a multiple stages in pipeline, right? You see these things. Whereas in superscalar, what happens is you actually have a two independent hardware, and each one is a pipeline. Okay, so this one is a hardware, first hardware pipeline, and this one is for the second pipeline hardware. Okay. Again, in this case, since you are using a pipeline, of course you need to worry about the dependency. Okay, every time you use the pipeline, you have to remove the dependency. If there is a dependency, then everything is messed up. Another technology is called the VLIW, very long instruction word. This actual technology is often and pretty popular in DSP, digital signal processor. Okay. DSP, some of you probably heard about DSP, but DSP is another processor. Like a Intel processor, this is a microprocessor. We have an 8051 microcontroller. We also have another processor called the DSP, digital signal processor. Okay, then what is a DSP? What's the difference between the DSP and regular microprocessor? The main difference is that this microprocessor is to do any job, basically. This is not just for any specific purpose. Okay? Microprocessor in general is for user PC. Using this PC, you can run Windows, you can do whatever you want. Okay? Generic purpose. However, in DSP, okay, digital signal processor typically is a specific purpose. Okay? DSP is for specific purpose. For example, in your cell phone, right? Your cell phone has a DSP. Each of your cell phone or smartphone has a DSP. And sometimes there are not just one, but a couple of the DSPs, maybe two DSPs or something like this. And one of the purpose in your cell phone, okay, and one of the reasons why you need a DSP is to do a processing of your voice. Okay, when you use a smartphone or your cell phone, right, you talk. And your voice goes into DSP, and DSP actually do an encoding of your voice. Okay? So encoding actually is a lot of computational intensive, meaning that you need to do a lot of job, a lot of multiplication, addition. There are a lot of calculation, okay, in encoding. Okay? So mathematically, it's very challenging. Okay? There are a lot of things to do. So such kind of addition, multiplication, and a lot of things will be done in DSP. And DSP is designed specifically for such kind of calculation. You can do the same thing with the microprocessor, but DSP is actually faster because we actually designed the DSP processor to do such kind of calculation. So we have an additional hardware in DSP to do such things, addition, multiplication faster. Okay? So using DSP is faster for that, a lot of calculations. One of the main popular things is FFT. I guess you didn't learn the DSP course yet, right? So next semester you're going to learn the FFT and things like this. You know the Fourier transform, right? Fourier transform you probably learn in mathematics course, but in next semester you're going to learn the DSP. And in DSP, using this DSP processor, you calculate the FFT or the Fourier transform. Okay? So to do the Fourier transform, you do a lot of calculation. Okay? So the DSP basically is specifically for such things, calculation. So in DSP processor, this technology is popular, VLIW. So let's understand what this means. A very long instruction word. It's actually very simple to understand. So far, we learned that there are a lot of instructions. Some instruction is short, like what? Like a clear A. That's very short, right? That's very short instruction. But there are actually some other instruction is pretty long, like some of the branch, DJ and Z. Then in that case, DJ and Z actually needs multiple operands, right? So that actually is a little bit long instruction. So each of them is just one instruction, but some instruction is short, some other instruction is a little bit longer. And when you have a code, assembly code, you have all the instructions, one after another, right? And so far, what we assumed was that when you compile, when you run the assembler, then each instruction is going to be assembled and make one instruction in binary, and another one becomes binary, and each one of these will be fetch, right? So the microprocessor, going back to this one, right, fetch, what we do is that we have instructions, one instruction, another instruction, and when the microprocessor fetch the instruction, we are going to fetch one instruction, one by one, right? When you fetch it, you always fetch only one instruction, right? We have a lot of instructions, like a clear A, add A, R0, move A, something like this, right? You have multiple instructions. Then when the microprocessor fetch it, we're going to fetch one instruction, and next time we're going to fetch next instruction. We're going to fetch only one instruction at a time. Okay, only one instruction at a time. That was what we have so far. But in VLIW, here's the difference. Look at this one. In here, we have 64 bits of long instruction. This is 64 bits. In this 64 long instruction, inside here, you actually have multiple instructions. Some instruction is short, actually very short, and some other instruction is pretty long. So in fact, inside the 64, you actually have multiple instructions. In this case, in this first example, you have 5 instructions, 5 different instructions. So maybe the first one here is like a clear A. Maybe the second one is like a add A R0, something like this. Okay? So you have 5 different instructions in one packet, simply speaking. Okay? So this is called a very long instruction word. So this is word, but it's very long, right? And in one word, you have 5 different instructions sometimes. In the second example here, you have another word, 64 bits word, but in this case, the instruction here is a little bit long instruction, so you only have 3 instructions. Okay, I'm showing you only example. So putting the multiple instructions all together in order to make one long word. And now what microprocessor does is that microprocessor does not fetch instruction. Okay, that was what happened before, but in this technology, microprocessor will fetch word. Okay, microprocessor does not fetch instruction, but instead, microprocessor will fetch the word. So when you are in the fetch stage, this is again, it's like a pipeline. Okay, we are still in a pipeline. So when you are in the fetch stage, microprocessor is fetching this word. Okay, I'm trying to give you the comparison. In earlier, okay, not this one, but earlier, what we did is that when you fetch it, you're going to fetch only one instruction, right? And then execute it and decode, execute. And next time you're gonna fetch the next instruction. Okay, you're gonna fetch only the instruction by instruction. But in this case, you are not fetching instruction, but instead you are fetching word. Okay, so this whole word, 64 bits, you are fetching this 64 bits. But inside these 64 bits, how many instructions do you have actually? You actually have 5 instructions, right? So when you fetch it, you are fetching this whole thing, 64 bits, and decode it. And when you decode it, you realize that there are 5 instructions. So therefore, you are executing 5, all at the same time. Okay, that's why we have all the execute. at the same time. All these 5 instructions are executed at the same time. And then save the result back to the memory. And this one actually has a multiple stages, like a pipeline. Okay? So this fetch is not fetching one instruction, but fetching the whole word. But inside this word, you have a multiple instruction. So you bring this whole thing, fetch, and execute it multiple times in parallel. That's the VLIW. So this is a popular one in DSP processors. Okay. The problem of this technology looks like it's pretty good, right? Because otherwise, in the previous, okay, in the conventional processor, as I said, you fetch instruction by instruction, but in this case, you bring all together. So it looks like it's better. However, because of this VLIW, something needs to be changed. Okay? What needs to be changed? Think about it. For you, right? When I write the assembly program, okay, I'm a programmer, so I write the assembly program. Should I change the different program for this processor? So this is a one type VLIW processor. There's a regular processor. Okay, there are 2 different processors. So should I write a different program, assembly program? No, right? I should not worry about VLIW or regular processor. So my assembly program is the same. Okay, I have the same assembly program. I have a lot of instructions in my program. So assembly is same. But hardware is different. This is different hardware. So who's going to deal with all the differences in hardware? So in this case, see here, we need to have a different compiler. So you have your own assembly program, right? With your assembly program, you run the compiler. In this case, we call that as assembler, right? Assembler, basically, what is the basic function of assembler? Assembler read your program, okay, and change that into binary. That's what assembler does, right? Assembler basically read your program and convert that into binary. So in this case, since we are using different technology, you need to use a special compiler for this hardware. Okay, so this is not the regular compiler. You need to use the compiler for this hardware. Okay, so this hardware needs a special compiler or assembler. And what that assembler does is that my assembler program is the same, but this compiler, this special compiler, read my program and bring all the several instructions together to make this word. That's what compiler does. So compiler will make this word. And now the compiler make this word, then what the hardware does is that hardware simply read this, fetch it. That's what hardware does. So all this job, okay, grouping of instruction, this is all done by the compiler or assembler. Okay, so you need to have a special compiler. So there's no compatibility with the existing software. Software meaning compiler in this case. So your assembly code is same, but you need to do the recompilation using special compiler. Okay, you need to have a special compiler because our hardware is different. I think I mentioned this one earlier, but think about that going back to a regular pipeline. So as I said earlier, one of the things that you want to worry about is when you're using pipeline is that you need to avoid dependency. Okay, so if in the first instruction, if you are using accumulator, all the other instructions you should not use accumulator because instructions need to be independent. Another thing that you need to worry about when you use a pipeline is the branch instructions. What is a branch instruction? Like a jump or if else, okay, something like that. That's a branch instruction. Why is that? why branch instruction is a special in pipeline. Think about this way. Let me write it in C code because that's easier. Let's say in C code, I have some, let's say there's A somewhere here, and let's say in C function, I have something like this, and let's think about a simple example like this, right? In this C code, you have some program up here, and in here you have some calculation, and you get the value A, okay? And in this if-else statement, you first check the A, and if the value in A is less than 5, then you go to here, right? And you execute these lines. But if the A is higher than 5, then you jump to here and you execute here. So what happens is, if you execute line by line and reach here, now then you know the value A, so you can jump here or there. But let's say you suddenly come to here, okay? What that means is, so we have a C program, and what the compiler does is the compiler basically compiles each of these lines. And do you think the compiler can find out whether you can jump to here or there? Compiler never knows, right? You have to run this. Only when you run it, then at that time you know, go here or there. Because in this case, right, there's some condition. Maybe maybe you read some hardware somewhere. Maybe there is some keyboard, and when you touch the keyboard, when you push the keyboard, then maybe B equal to 4. So in that case, A becomes 5, so you go in here. But if you don't push it, then B equal to 0, then A becomes 1, so you come here. So whether you push the button or not, sometimes you come here or sometimes you go there, right? So when you compile, then you don't know. You don't know, you never know you're going to jump to here or there. Okay, after you run it, only then, now depending on the case, depending on when you push the button or not, jump, sometimes you come here, sometimes you come there. So compiler never knows. You cannot expect. Same here in assembly. You have assembly program like this. So in assembly program, you can never expect. Okay, you can never guess whether you can jump it here or there. Okay, in that case, how can you use a pipeline? In order to use the pipeline, okay, in the pipeline, what happens is you have a lot of instructions, and first instruction bring it here, and second instruction bring it there, right? That's what you do. You fill each instruction per each stage, but that's only true when you have a lot of instructions sequentially. Okay, when you have a lot of instructions sequentially, then you can actually put each instruction here and here, no problem. But let's say you have somewhere here, you have if statement like this one. When you have if instruction, then I don't know. The assembler or compiler never knows whether you can go there or there. So in that case, how can you fill up the pipeline? You cannot. Do you understand what I'm saying? Okay, you never expect. So that's why in case of pipeline, okay, if you have some branch instruction like if, okay, then you cannot fill up the pipeline. Because I don't know, maybe you can jump here or there, I don't know. So since I don't know which instruction is going to be next, I cannot fill up the pipeline. So in that case, the pipeline will be empty. When you have a pipeline is empty, now you have a lot of performance loss. because we have this hardware to improve the performance, okay, in order to run the multiple instruction at the same time. But because of that instruction, branch instruction, we cannot fill up this pipeline, so we have to make it empty. So the performance is suddenly slow down. Okay? So that's very bad. For pipeline, branch instruction is so bad. So that's why the people, microprocessor designers, okay, they bring out this technology. So what this means is a branch prediction. So the idea here is these things. Compiler never know whether jump is here or there, but they're gonna predict. Okay? You can always predict. Maybe prediction can be like tossing a coin. Maybe you could just select random. It's gonna be here or there. So possibility maybe is half, right? You just pick anyone. Okay? That's possible, right? You just pick anyone. Then probability that your guess is right is half, because we have only two choices. So that's one way of a prediction. Maybe that's a little bit stupid prediction, right? What is a better prediction? Better prediction is that this is not the old code, right? You have like millions of other lines, a lot of other lines. Okay, so based on the other lines, this compiler, this is what happened inside the compiler. Compiler basically collect all the history. Okay, there are a lot of other lines up here, like a million lines up here. So based on a lot of other history, okay, you basically collect all the statistics. Okay, at this time, looks like we jumped into there, and some other part you jumped to there, so you basically count. Okay, maybe so far we have 1,000 branch instructions, but out of these 1,000 instructions, maybe 600 times you jump there, and another 400 times you jump there. Okay, something like this. It's like statistics. Based on that, okay, looks like it's more jumping to this time, more jumping to here, because out of this 1,000 times, we jump to 600. Okay, so it's like more jumping to here, right? So at this time, maybe it's it's higher probability that it's jumping to there, because so far we jumped there more times. Something like this, right? So you actually collect all the statistics and expect and predict a little bit more smart way based on all the history. Okay, that's based on statistics. That's what people do. So that's branch prediction. So nice thing about branch prediction is that when you predict that maybe with a higher probability we're gonna jump to there, and you just predict it that way, then what you can do? What you can do is that you predicted that in the if statement you jump there, then there are instructions here, right? And you put this instruction and put that into a pipeline, because you expected, you predicted that in this branch instruction you're going to jump to there, so this would be the next instruction. After this one, that would be the next instruction you execute, right? Because you jump to there. So bring this instruction and put that into the pipeline. Okay? That's what you can do in the branch prediction. So your pipeline is not empty anymore. Your pipeline is still full. However, your prediction may be incorrect. Sometimes your prediction is wrong. If your prediction is wrong, let's say you predicted that, okay, in this branch instruction, I'm going to jump to there. So let's bring this instruction and put that into a pipeline. However, later, when you execute this one, actually, your guess was wrong. They actually jumped to there. In that case, what should happen? Your pipeline has wrong instructions, okay? Because you already put this instruction into a pipeline, but that was wrong. So suddenly, you need to empty all the pipelines instructions. So all the pipelines are now suddenly you remove all that. Okay? You completely clear all the pipelines, and then these are the actual instruction you need to have. So put this instruction now in the pipeline. So there will be a performance hit, meaning you have a loss, performance loss, because your prediction was wrong. Okay? But if your prediction was right, okay, if your prediction was right, then there's no performance loss because the right instruction is already in the pipeline, so you can just keep going with no performance loss. Okay, that's a nice thing about this branch prediction. Processors has a FPU, the floating point unit. In order to discuss this one, we need to understand the terminology like fixed point and floating point. In DSP processor, again, a regular DSP processor, you often hear the fixed point DSP and floating point DSP. Okay, this is very common word. Okay, you need to understand, you need to remember this one because you're gonna hear this one many times. Fixed point DSP basically means that, let's say you have an 8-bit word, then those 8 bits is integer value. Okay, that's a fixed point, like an integer value. So for example, right, let's say you have 8-bit. In this case, since we use that as an integer, the last bit, LSB, is going to be 2 to the 0. This one is 2 to the 1, right? That's how you read it. And the MSB is 2 to the 7. Okay? That's how you read it. That's a fixed point. Simple, right? We always use it this way. So that's fixed point. However, in the floating point, it's different. In floating point, we read it actually different. This is actually a floating point format. How to read this floating point actually is a little bit complex, a little bit more complex. I guess maybe the next DSP course, I think that we can probably cover this. But there is an IEEE standard how to read this fixed point. But this fixed point is not like a 2 to the 0 or 2 to the 1, 2 to the 7. There is a formula how to read this. But the reason that we need a floating point DSP like this is because that sometimes you want to have the floating point value. Floating point value basically means that fractional value, like a 2.1756, something like this. Okay, sometimes you need this value, right? Many times actually. So because of that, some of the DSPs support the floating point expressions, like this one. So at this point, I think that you just remember that there is a fixed point DSP or processors, and there are floating point processors. Okay, you can just remember those things. How the details about floating point will be covered in next semester in the DSP course. We have some details coming up in that course. Okay. Okay, this one is actually easy one. You can just you already know some of these things. So it says a new technology Intel processor. Remember that on the first week of this course, right? First lecture, we looked at the history of microprocessor. Remember that? We looked at the history, right? And in the history, what we looked at was that maybe in 1960, 1970, 80, up to the 2000, the main thing when you develop Intel, actually Intel is the main company, right? The major company. These companies are always trying to increase the clock speed, like 100 megahertz, 1 gigahertz, 3 gigahertz. They always try to increase the clock speed in order to improve the performance. However, based on the silicon, right now, we are at the stage where the clock speed cannot be increased anymore. So that's why in a certain like a mid-2000, the Intel and other microprocessor companies, they are trying to focus on other technologies. So speeding up, increasing class speed is not possible anymore. So that's why they are focusing on like others, like a hyper-thread, multi-core, multi-processor, okay, something like this, right? So that's why these kind of terms are now introduced in somewhere 2000 and mid-2000. Okay, in hyper-threading, it's like similar concept of multitasking or multi-threading, right? And this one actually has a similar has a relationship with the multi-cores. In multi-cores, it's like you have a CPU core, multiple CPU core in a one CPU, one physical CPU, right? So depending on the processor, sometimes the multiple cores are sharing the same memory, or sometimes each core has a different memory. So that depends on the processor. Okay, these are some other examples of processor. Some processor, laptop processor, desktop server. So why do you think the Intel actually categorized the processor into this way? Why do they call this a laptop processors, and why the laptop processor is different from desktop? Because each processor needs to be optimized differently, right? Laptop processors needs to be optimized to do low power consumption, right? Low power consumption is the main key. Laptop processor generally, or server processor, power consumption is not a problem. High performance, how many MIPS? You know MIPS, right? Mega instruction per second. How many MIPS you can have? How many MIPS you can execute? That's the main thing in this processor. So definitely you want to optimize it different way. So they name it differently. The last thing that I want to introduce you is this processor called ARM. Okay, ARM is the name of the company. It's the UK-based company. Okay, and this is a global company, but it's originally in UK. In 1985, in history, this computer group developed RISC processor. You know the RISC, right? We learned the RISC. It's a reduced instruction, okay, processor. And in later, they changed the name of the company called ARM. Okay, so now the ARM processor was developed in somewhere in 1980, late 80s. Okay, and so far this ARM is the best, is the most popular company in microprocessor. You know that the Intel is probably the major company in microprocessor. That is true in the PC platform. Okay, personal computer. In the PC platform, Intel is the number one, but we have a lot of electronic devices these days, right? PC is just one of them. What kind of electronic devices you have? Like a cell phone. We have so many cell phones. Each of you have old cell phone, right? A smartphone. Each of you have smartphone. Do you think Intel processor is in there? Your cell phone does not have Intel processor, right? Intel processor is in your PC, but not in your cell phone. Then what processor do you have in your cell phone? Cell phone has a processor, multiple processor actually. One of the processors is this one. So think about it. How many cell phones do you have in the world? I mean, so many, right? You have so many of this processor. This is so big company now, so popular, right? Pretty much everyone. I think the ARM processor has the penetration rate of almost 80 to 90%. So if you look at the cell phone worldwide, probably 80 to 90% of the cell phone used ARM processor. So big company. Okay. So that's why we probably want to know. Okay, want to know these things. If you join Samsung or industry, you probably hear about ARM processor many times. So this is opportunity to learn this one. So ARM, based on the history, they do this and do that, but Most important thing is they developed the RISC processor. And in ARM processor, this is not actually a processor. And Intel, right, they developed the processor, okay? And processor, and what you need to do is buy the Intel processor and put that into your motherboard, and that's going to be a PC. But in ARM processor, okay, they are not developing the final processor. That's why you probably didn't heard about that. You probably heard about maybe Samsung processor. I don't know. Maybe you heard the Qualcomm processor. You heard of Qualcomm, right? Qualcomm has a processor. Qualcomm developed a processor. That's true. But if you look at the inside of Qualcomm, okay, this is a chip. And if you actually look at inside the Qualcomm chip, this is the inside. This processor is the inside. So their business, I'm talking about the company, this ARM, their business is not to develop the final processor, but they actually developed what they called as IP. Okay? They're not making the final chip. What they're making is the product, IP. And this IP is nothing but a just program. And they sell this processor architecture. They only sell the architecture. They're not making chip. So they sell this architecture to other companies like a Qualcomm or Samsung. Samsung, they use a lot of them, a lot of ARM processor. Okay? So they're only selling the architecture. And Qualcomm basically buys this ARM processor architecture and bring that into their own Qualcomm chip. So it becomes, finally, it becomes a Qualcomm chip. But inside that, they have this processor. So this is actually, that's why, since this one is inside the Qualcomm, you probably hear of the Qualcomm, but maybe you didn't hear the ARM. Okay? But this is actually a very big company, very major company. Okay, so these are some of the details of the history, but let's look at a little bit more about the ARM processor. This is again RISC processor, and that's what we call as a SoC, right? You heard about SoC, system on chip. Inside the chip, you have a system, and this system, this architecture is inside the chip. This is actually very special in the sense that it is a 32-bit RISC processor. Okay, now we are talking about 32-bit processor. And as you see here, ARM sells the synthesizable core. That's the official name. I said that they're selling architecture, but this is a more correct word. Synthesizable core. Okay, not the chip. They're not selling chip. Okay, they're selling only the core, synthesizable core. And Qualcomm buys the synthesizable core and put that into their product. Okay, and synthesize it and making their own chip. And this is one of the brief picture. In ARM processor, there are two different modes. Okay, thumb mode and ARM mode. In ARM mode, this processor basically behaves as a 32-bit. Okay, this is actually 32-bit processor. But you can run this one into a 32-bit processor, or if you want, you can run this one into a 16-bit processor. This is a 32-bit processor, but you can run this one into the 16-bit processor, if you like. Okay, sometimes there's a reason, actually. There is a reason, but you can run that into a 16-bit processor. It's called the thumb mode. These are the memory system that it can support. Why this is a 4 gig addressable space? I think this one we already talked about maybe in the first week or second week, right? What is the addressable space, address space of 8051? How much was the address space in our processor? 64K. Why 64K? Why? Because we have 16 address pins. Okay? We have 16 address pins. 2 to the 16 is 64K. Then in ARM processor, we have 4 gigabyte of address space. Why 4 gig? Why address space 4 gig? Because we have a 32-bit. address pins. Okay, so 32-bit means 4 gig. 2 to the 32, 2 to the power 32 is 4 gig. Right? So that's why 4 gig. This is a little bit more details, and there is an operating mode here, and there are a lot of mode. But as you can see here, okay, what I'm trying to introduce you here is a little bit more detail about 32-bit processor. Okay, in this course we learned 8051, 8-bit microprocessor, right? So as I mentioned earlier in the first week, some of you may want to ask a question. We have a 32-bit processor these days. Why are we learning 8-bit, like a 30-year-old processor? Maybe some of you asked that, right? So here's the reason. 32-bit processor is so complex. You see that this is an actual 32-bit processor used in your cell phone. Your cell phone has this processor. It actually has a lot of operating mode, user mode, interrupt and fast interrupt, supervisor, abort, and system. There are a lot of different modes. So what that means is if your processor actually has a lot of pins, it's like several hundreds of pins. Okay? Using those pins, if you get a certain input, then this processor suddenly changes the mode. Like for example, right? Let's say you ask this processor to read some memory. So this processor go there and try to read the memory, and it looks like that memory is not existing. In that case, what should happen? You want to try to read the value from a certain memory address, but that address, there is nothing. In that case, suddenly the microprocessor goes to the abort mode. Suddenly it changes to abort mode because that's an error. Okay? Something like this. Depending on the mode, depending on the situation, the processor jumps into another mode. For example, right, when you get an interrupt, then this processor suddenly jumps to interrupt mode. Okay? So in the processors, they actually change the mode depending on the environment. This ARM processor has 37 registers. In our 8051, we have some number of process registers, but in ARM processor, there are a lot of registers. And out of these 37, 31 registers are general processor. Okay? You can use whatever you want. For us, we have R0, R1, R2, those things, right? That's a generic registers. Same here. In ARM processor, there are these number of registers, and each register is 32-bit. Okay, in our processor, we have 8-bit register, right? In this case, you have a 32-bit registers, but these many. So these registers, you can use whatever you want. And there are 6 different status registers. Do we have a status register in 8051? We have, right? In the status register, you have a flag, carry flag, overflow flag, and those things, right? In ARM processor, there are also status registers, many of them. And there are also 15 other general registers, R0 to R14. Okay, there are other processors, also the registers, general registers. And there are also others. So depending on the mode, okay, we have a lot of mode. We discussed in the previous slide, right? We have many different modes. So depending on the mode, you have a different registers. If you are in the user mode, then you have like 32 registers. But if you jump to service mode, suddenly you have only 20 registers, something like this. So number of registers and what register you have now changes depending on the mode. Okay? You are in a different mode, then you see the different registers. Sounds very complex, right? It's pretty complex. So here's one. See that these are the general registers, R0 to R15. R15 is actually a program counter. So the R0 to R14 is what you can use. And here, you see that this is a shaded, right? This is a little bit gray, meaning that this is not regular registers. These registers will be only visible when you are in this mode, FIQ mode. When you are in FIQ mode, now you have these registers. Okay, something like this. System modes only, right? This is usable in user mode. When you are in user mode, you can have these registers, but in other mode, you have other registers. And see that you should have a stack pointer, right? This is the same as our stack pointer. Every processor, you should have a stack pointer. So in this case, in ARM processor, R13 is a stack pointer. And there are program counter also. Okay, in our 8051, we also have a program counter, right? In ARM processor, there's also program counter. This one also has a link register. There are other special registers like this one and this one. So the details I'm not going to talk about, but it's pretty complex. You have a manual like this big for this processor. What I'm trying to introduce you is that this is the most popular 32-bit register we use these days. So some of the details, let's skip this. This exception vector is something exactly same as our interrupt vector. Remember that we have interrupt vectors, right, in 8051. Here, this processor has the same thing. In this processor also, right, now remember that we have an address like this. This is 32-bit address. You see that this is 32-bit, right? We have we have 8 nibbles, right? This is 32-bit. So in 32-bit address, we have a 0000, 0000. This is the first address. Okay, when you reset, then always the processor goes to here. You always start from here, right? That's why we call this a reset vector. Remember that? We have the same concept in 8051. So this is a reset vector. See the reset, right? And in this processor, in the address 4, you have another vector called undefined instruction vector. What that means is if you want to execute some instruction, but that instruction is not defined, then suddenly it's error case, right? When you have error case, suddenly you jump to here. Microprocessor has an error, this error, undefined error, suddenly it jumps to this vector. Same way, software interrupt. When the software interrupt happens, then you should jump to here. This is the vector for this case. Abort vector and reserve vector. This is the interrupt vector, IRQ. This means interrupt. Okay, so this processor has the interrupt vector here in this address. But this one has another interrupt called the FIQ. Okay, fast interrupt. So now then, what is the difference between the regular interrupt and fast interrupt? Why do we call this one as a fast? It's actually interrupt. This is interrupt. This is another interrupt, basically. But only difference is that this is what they call as a fast interrupt. Why do you think this is a fast? Here is the reason. Very simple reason. Generally, as we discussed in the interrupt, what happens is when you get an interrupt, right? Then suddenly you jump to interrupt vector, which is something like this, right? And inside the interrupt vector, what instruction do you have? You have a jump interrupt service routine. That's the instruction you have, right? You're going to have jump instruction here, so that when you get an interrupt, you jump to interrupt vector, and instruction here is again jump, so you actually jump again to the interrupt service routine. That's what happens regularly. But in this fast interrupt, what happened is that you get an interrupt again, and you jump to this interrupt vector, fast interrupt vector, and remember that this is actually the last one in this vector. This is the last one, right? There is a reason why the fast interrupt is at the last. Since this is the last, what you can do is that you don't have to jump to actual interrupt service routine. Your interrupt service routine can be right here, just next to it. Because this is the last one, your interrupt service routine can be here. In that case, you don't have to jump, right? You can just go down. That's actually faster because you don't have to jump. A little bit faster, a little bit, right? So that's why we call this a fast interrupt. That's the difference, okay? So these are the we call that as an exception vector, but the same concept we have it, like an interrupt vector. Okay? So that's pretty much the introduction of ARM processor. Okay, any question?